Lighthouse Scientific Education presents a lecture in the Solutions and Water series. The topic, Intermolecular Forces. Material in this lecture relies on an understanding of the previous lectures, fundamental properties of matter, bonding and overview, covalent bonding, and ions and isotopes. The lecture begins with a brief description of intermolecular forces to give some perspective of the subject. It includes bonding types already familiar to the student and a helpful look at how to evaluate trends seen with intermolecular bonding. Before deepening the investigation, there will be a review of the properties of matter that underlie intermolecular forces. An extensive review is given due to the advanced nature of the topic. Students who have a strong foundation in the subject matter of ion formation and polarity should skip ahead to the ranking of intermolecular forces. The review includes a look at atomic forces. Since the same forces are at work at intramolecular bonding that are found in intermolecular bonding, it will be helpful to look at the role of electronegativity and polarity. Building on the review is a progressive discussion of intermolecular forces. Moving from strongest intermolecular forces to weakest, there is ion-ion, ion-dipole, hydrogen bonds, dipole-dipole, ion or dipole-induced dipoles, and finally, London or dispersion forces. To give some perspective to intermolecular forces, we can ask, what type of bonds have we come across so far in our studies? Mostly we've seen intramolecular bonding, with the term intra meaning within. Intramolecular bonds hold atoms together within a molecule or compound. To a lesser degree, we've seen intermolecular bonding, with inter meaning among or between. Intermolecular bonds are between compounds or elements. For the most part, intramolecular bonds are stronger. It then follows that intermolecular bonding is relatively weak. Covalent, metallic, and ionic are types of intramolecular bonds. The carbon-hydrogen bond in methane is an example of a covalent bond. The delocalized electrons around a core of metallic nuclei with their inner shell electrons is a representation of metallic bonds. And the crystal lattice of solid sodium chloride serves as an example of ionic intramolecular bonding. The ionic bonding type actually finds itself straddling both the definition of intra and intermolecular bonds. That is, depending on the context of the discussion, it can be considered in either camp. When an ionic bond is spoken of as a compound, then the interaction between ions is within and intramolecular. But an ion itself can be considered an entity on its own, and then an ion-ion interaction is between particles and intermolecular. As we see, the strength of an intermolecular bond is for the most part based on the charge, permanent or temporary, of the participating species. If we look at the cast of characters that are involved in intermolecular bonding, the one that makes the strongest bonds is the ion. Ions have a large permanent charge, which readily interacts with its neighboring particles. Other players include the permanent dipole. Although it has a weaker charge than an ion, it too readily interacts with neighboring particles. The only really new character in this lecture is the induced dipole. It is a short-lived dispersion of charge, and it is found in almost all matter-matter interactions. All three of these species will be discussed in detail, along with the interactions found by pairing these three in different combinations. Some terminology clarification is useful at this point, starting with intermolecular forces. They are the electrostatic attraction or repulsion of charged particles, charge being positive or negative. The charges can be full charges, as seen on ions, or partial charges of dipoles. As such, the strength of an intermolecular force is dependent on the size of the charges. Larger the charge, stronger the force. Weaker the charge, weaker the force. And then there is the intermolecular bond. These are the electrostatic interactions between different atomic scale particles. That includes elements, ions, and compounds. When dealing with two particles, intermolecular bond intermolecular force, and intermolecular interaction are generally talking about the same thing. To give some perspective on the role of intermolecular bonds in chemistry, we will look at the trend these bonds produce in phase transition. More specifically, the effects of intermolecular bonding can be tracked by following the temperature of phase transitions. Water will stand in as an example molecule, and its three familiar phases are solid, liquid, and gas. A phase transition is moving from one of the phases to another and can be viewed as the making or breaking of intermolecular bonds. The molecules that make up ice, liquid water, and steam is H2O, and it is not itself changed in moving between states. The states are based on the degree to which the water molecules interact with each other. All things being equal, with the addition of heat, there is a characteristic temperature at which ice melts. It's called the melting point. There's a characteristic temperature at which water boils. It's called the boiling point. There's also transitions that occur with the removal of heat. In the Fundamental Properties of Matter lecture, it was argued that adding heat adds motion to the molecules, and transitioning from solid to liquid occurs when the energy of motion exceeds, to a certain degree, the energy of particle-particle interactions, intermolecular bonds. When enough of these intermolecular bonds have been broken, the particles begin to slide past each other. That is liquid. When enough additional heat is added to break all of the intermolecular bonds, the particles fly apart. That is gas. Since the melting and boiling points reflect the balance between the intermolecular forces between the particles and the energy of motion due to the heat, it reasonably follows that the stronger or more intermolecular bonds will push melting points and boiling points higher. Stronger intermolecular interactions require more energy or heat to break the bonds that are necessary for phase transition to occur. In short, substances with strong intermolecular forces melt and boil at higher temperatures than substances with fewer such forces. As always, there are other factors that come into play. Geometry can most certainly affect melting and boiling points of a substance. Phase transition is useful in giving context to intermolecular bonding. Now we're going to step back and build up the foundation of intermolecular forces, starting with a review of how and why atomic scale particles interact. That means going all the way back to the structure of the atom. Consider two atoms, atom A and atom B. Drawn here are just the positively charged nuclei of the atoms. But atoms also have negatively charged electrons zipping about in shells around the nucleus. Often, this is shown as an electron cloud. Now, electrostatic interactions result from attractive or repulsive forces between atoms, ions, or compounds. That is to say, the negatively charged electrons in atom A are attracted to the positively charged nucleus in atom B. Also, the negatively charged electrons in atom B are attracted to the positively charged nucleus in atom A. Conversely, negatively charged electrons in atom A and B repulse each other, and positively charged nuclei in atoms A and B repulse each other. Opposite charges attract, like charges repel. Ultimately, all atomic scale interactions are going to come down to a combination of these four electrostatic interactions. As long as there is a net attraction between particles, some form of bonding will occur. Furthering our development of a base for intermolecular forces is a review of what we know about intramolecular bonds. The interaction between molecules and compounds will to a large degree be determined by what type of intramolecular bonds. From the Bonding and Overview lecture, we remember that intramolecular bonds can be broadly categorized as covalent, polar covalent, or ionic. What distinguishes the bond type is how well they share electrons. Importantly, sharing means time. How long does one atom in the bond keep the shared electrons compared to the other atom? Using a graphical representation of sharing between hypothetical atoms A and B, in a covalent bond, electrons spend equal time or near equal time around atom A and B. In polar bonds, the sharing is less equal. Electrons spend more time around atom A than B. This uneven distribution gives a rise to a dipole which can participate in intermolecular bonding. And for ionic bonding, there is no sharing. Electrons spend all their time around atom A. The transfer of electrons from B to A causes the formation of ions. The charged ion is a potent player in intermolecular bonding. How do we decide which category to put in intermolecular bond? Quite simply, it falls to the electronegativity of the atom in the bond. Electronegativity, or En, is the capacity of an atom in a molecule to attract shared electrons from another atom. Your textbook should have a periodic table that has laboratory determined En values for most of the atoms. Electronegativity has been covered several times before, but is of such importance that we will quickly run through how the categorization of a polar or ionic bond is made. Delta En is the difference in electronegativity between atoms in the bond. That value is compared to a scale that indicates the bonding type. For instance, take the oxygen-hydrogen bond. The difference in electronegativity is found by getting atomic specific values from the table and subtracting the smallest from the largest. Oxygen's value is 3.5. Hydrogen is 2.1. 3.5 minus 2.1 is 1.4. Taking the 1.4 to the scale shows the bond to squarely be in the polar covalent bond region. While we're at the polar bond, let's further explore what the uneven distribution of electrons means in the context of all the bonds in the molecule. Take water, for instance. It has two polar covalent bonds, with a larger electronegative atom, oxygen, keeping the electrons from the bond for more than half of the time. What that means, from a net charge perspective, is that oxygen will have more negative charge than it started with as just an atom. It will adopt a partial negative charge, as denoted with the lowercase Greek delta symbol. If the oxygen has more of the negative charge, then the hydrogens will have less negative charge than they started with as an atom, and each will adopt a partial positive charge. To give some perspective, a partial negative charge is much less than the charge on an electron, and a partial positive charge is much less than the charge on a proton. The partial charges are significantly weaker than the charge on an ion. Also keep in mind that while there is a distribution of charge, there is no net charge on the molecule. It has the same number of electrons as protons. The amount of partial positive charge is equal to the amount of partial negative charge. To put this in context of intermolecular bonding, we need to bring in the term electric dipole. It is a separation of electric charge. The first oxygen-hydrogen bond is an electric dipole because positive-negative charge is separated in space, as is the case for the second dipole bond. These are called permanent dipoles because the electronegativity of the atoms calls for an uneven distribution of electrons. As was seen in the covalent bond lecture, these two polar bonds sum to a net dipole or a molecular dipole. Water is a polar molecule because it has a net dipole. In this lecture, and in many textbooks, a molecular dipole is given the cartoon representation of a flattened oval, with one side carrying the partial negative charge, and the other the partial positive charge. Often, a color scheme is applied that has partially positive end colored blue and the partially negative end colored red. In between is considered neutral and is purple. The color scheme allows the distribution of charge to be seen at a glance. It is really a useful tool. That sums up the foundation component of the lecture. It is now time to look at intermolecular forces and bonding, and we will do so moving from strongest forces and bonds to the weakest. The ion produces the strongest of the intermolecular forces. The ionic bond is an electrostatic attraction. The positively charged cation is attracted to the negatively charged anion and vice versa. The charges are full charges. That means that they are at least a +1 or a -1. These charges are much greater than the partial charges associated with polarity. Because of the size of their charge, ionic interactions are considered the strongest of the intermolecular forces. We will put them at the top of a list which ranks the strength of these forces. Not all ionic interactions have the same force. A couple trends can be established that allow the strength of interaction within this ion-ion category. A look at the left side of the periodic table shows us where some of the more common cations come from. Column 1 elements form +1 cations, and column 2 elements form +2 cations. the size of charge plays a big role in the strength of intermolecular bonding for a substance. This can be shown graphically using phase transition. The y-axis is the melting point of an ionic compound, and the x-axis is the size of the charge. As seen with the periodic table, ionic charge increases going to the right. Since the melting point reflects the temperature at which the energy of motion exceeds some of the intermolecular forces, it is reasonable to expect that the larger the charge, the stronger the intermolecular bonds, and the higher the temperature needed to melt the substance. A second factor in the strength of intermolecular forces in ionic bonding is the size of the ion. The argument has it that the larger the ion, the more volume it has to disperse its charge. Larger ions of the same charge make weaker ionic bonds. On the periodic table, ionic radius or size of the ion increases going down the table. Plotting size of ion for any one particular size charge on the x-axis should give the opposite trend, since the bigger ions have smaller intermolecular forces to overcome and less heat is needed to do so. To summarize the trends: higher charge, higher melting point. Bigger ion for the same charge, lower the melting point. Same set of arguments can be used with boiling points. Moving down in strength is the ion permanent dipole intermolecular interaction. It is the attraction of the full charge of an ion to the partial charge of a dipole. Since a dipole has both a partial positive and a partial negative charge, it can form favorable interactions with either a cation or an anion. Strength of the interaction is dependent on the magnitude of the charges on the ion and the dipole, and the size of the ion. Larger the ion, smaller the force. Both of these factors were used to describe the strength of an ion-ion intermolecular bond. Since one of the components in this type of intermolecular bond is an ion, it stands to reason that the same set of factors are still relevant. The ion permanent dipole intermolecular bond will rank second on our list because of the strength of the charge on the components. A second consideration with this type of intermolecular bond has to do with the dipole having both partial positive and partial negative charges. The ion charges determine the orientation of the dipole. The end of the dipole with the opposite charge faces the ion. This makes sense from the perspective of electrostatic interactions. If a cation found itself in the polar solvent water, how would a water molecule approach the positively charged ion so that it maximized electrostatic attraction but minimized electrostatic repulsion? It would orient itself in a manner that pointed the partially negative oxygen at the positive ion. In this way, it promotes the attraction of opposite charges and allows water to keep its partial positive end as far from the positive cation as it can. Other water molecules would do the same thing, and the cation would be considered solvated. The opposite happens to a negatively charged anion in water. Here the water molecule orients itself so that its partially positive side is pointed at the negatively charged anion, allowing an electrostatic attraction. Other water molecules orient themselves around the anion in the same manner. Ion-dipole forces are important in solubility. The term dissociation is used with ions dissolving in water. The lectures Ionic Bonding and Solutions in Solubility also cover dissociation. The next kind of intermolecular bond is a rather particular one. It is a variety of the dipole-dipole intermolecular bond. Dipole-dipole interactions are between two permanent dipoles. Hydrogen bonding, or H-bond, is a variety or a specific case of dipole-dipole interactions. It is always between an atom with a high electronegativity, like oxygen, nitrogen, or fluorine, in one molecule, and a hydrogen bonded to an atom with a high electronegativity in another molecule. These very strong dipoles make the hydrogen bond one of the strongest dipole-dipole interactions. They are so strong that they get their own place on the ranking, third on our list. Since dipoles have both a positive and negative end, there will be a favorable orientation of molecules that maximize attraction and minimize repulsion. The partially negative end of one dipole, atom with a high electronegativity, is oriented towards the partially positive end of another dipole, the one with the hydrogen bonded to an atom with a high electronegativity. While water is the most familiar example, there are others that we have come across, like ammonia, NH3. It fulfills a requirement for being capable of forming hydrogen bonds by having an atom with a high electronegativity, nitrogen, in one molecule, and a hydrogen bonded to an atom with a high electronegativity in another molecule. Same type of orientation is found in water. Since hydrogen bonding is so central to aqueous solution chemistry and biological chemistry, we should further investigate its attributes. Many of water's unique properties can be understood from the perspective of the numerous hydrogen bonds it makes. The Water Aqueous Solution lecture in this series covers the topic more in depth, but we will look at one property. That will be hydrogen bonds' role in the phase transition of boiling. Boiling point trends can be viewed as a function of the periodic table. The effect is quite stark. Consider three columns in the periodic table, headed by the elements carbon, nitrogen, and oxygen. For this demonstration, each element in these columns will be represented by its compound containing a maximum number of hydrogens. For carbon in its column, that is 4 hydrogens. For nitrogen in its column, it is 3 hydrogens. And for oxygen's column, it is 2 hydrogens. Of all these compounds, only NH3 and H2O make hydrogen bonds. Here's a graph of the boiling points of the 3 compounds in the 3 columns. Each column is its own trend line. Carbon's column shows that as the central atom gets larger, moving down the table, the boiling point gets larger. None of these compounds make hydrogen bond, and the trend is linear. For the column headed by nitrogen, a similar trend is expected, but there is a noticeable absence where ammonia should be. It has a noticeably higher boiling point. It takes more energy to overcome the hydrogen bonds in ammonia, and that leads to a higher boiling point. A similar pattern is seen with oxygen's column. Water is expected to boil at something like -80 degrees Celsius. The stronger intermolecular forces of its hydrogen bonding requires more heat, higher temperatures to be overcome. Water boils closer to 100 degrees Celsius. The take-home lesson here is that overcoming hydrogen bonds requires substantial amounts of energy. As mentioned earlier, hydrogen bonding is a particular form of dipole-dipole interaction. A separate category on the list of intermolecular forces is given to the general term dipole-dipole. Dipole-dipole is the interaction between 2 permanent dipoles. While there is a distribution of charge in these dipoles, they have a net charge of 0. The dipole-dipole intermolecular bond is between neutral molecules. This isn't strictly true, but we will limit our discussion to neutral molecules. Dipoles are depicted here as ellipses for convenience. As for orientation, the partial negative end of one dipole is pointed toward the partially positive end of another dipole. An electrostatic interaction. Furthermore, in a solution or mixture of dipoles, the most favorable arrangement is for the dipoles to orient themselves such that they maximize attraction and minimize repulsion. This is not unlike the orientation found with ionic compounds. But dipoles are much weaker than ions and have to be much closer in order to form intermolecular bonds. Still, they are strong enough to make it to 4th place on our list of intermolecular forces. Another similarity that dipoles have with ions is that the strength of the charge, partial with dipoles, and the geometry of the compound influence the strength of the interaction. The take-home trend for this intermolecular interaction is that the stronger the dipole, the more energy that is needed to break its intermolecular bonds. We saw that with the H-bond and the large effects on water and ammonia. Water's larger partial charges have more effect than ammonia's. So far we've been dealing with particles that we have some history with, ions and dipoles. They both have what is termed permanent charges. Now it's time to introduce a new concept, the temporary or induced dipole. All elements and compounds are susceptible to having induced dipoles. This phenomenon arises out of the very nature of the atom. With an atom, the distribution of electrons around the nucleus is symmetrical. The distribution of electrons around a covalent bond, nonpolar, is also symmetrical. Consider this drawing of a spherical electron cloud around its nucleus. The symmetrical distribution of electrons means that the atom as a whole is neutral. According to the charge bar, the atom should be colored a neutral purple. A similar argument can be made with the distribution of electrons around a nonpolar covalent bond. The two atoms in the bond are also colored purple because of the symmetrical distribution of electrons around their nuclei. Now imagine what would happen if a charged particle is brought near the atom or the covalent bond. Proximity to a charge, be it ion or dipole, distorts the symmetry of the electron cloud. Proximity to a charged particle induces a dipole. For instance, bringing an atom near a positive charge would induce a dipole because the electrons in the atom are attracted to the positively charged particle. The atom would lose its electron symmetry as the side of the atom nearest the charge would become electron heavy and adopt a partial negative charge. The other side of the atom would have fewer electrons than it did prior to the introduction of the positive charge, and therefore adopt a partial positive charge. Bringing the atom near a negative charge would also induce a dipole in the atom because the electrons in the atom nearest the negative charged particle would be repelled and pushed to the other side of the atom, making the far side adopt a partial negative charge. The side of the atom nearest the negatively charged particle would be electron light and adopt a partial positive charge. Same set of arguments work for bringing a nonpolar covalent bond near charges. As it neared a positive charge, electrons would be drawn to the charge, inducing a dipole. As it neared a negative charge, electrons would be pushed to the opposite end of the bond. The redistribution would cause an induced dipole. Induced dipoles are temporary. They will go away if the charged particle is removed. Induced dipoles are weaker dipoles than permanent dipoles. Still, induced dipoles and charged particles form intermolecular bonds. The partial negative charge of the induced dipole forms a weak intermolecular bond with a permanent positive charge. The partial positive charge of the induced dipole forms a weak intermolecular bond with a permanent negative charge. The weakness of the induced dipole has this form of intermolecular bond placed towards the bottom of our list. Although it is weak, it still requires energy to break. The strength of bond is related to the strength of the induced dipole, which itself is related to the strength of the permanent charge on the particle. Therefore, ions with their full charge will induce larger dipoles than will permanent dipoles. The size of the induced dipole is proportional to the size of the permanent or full charge. Since a full negative charge is much larger than a permanent dipole, an anion will induce a larger dipole. Likewise, a full positive charge is much larger than a permanent dipole, and a cation will induce a larger dipole. This can be summarized in a trend. The stronger the ion charge or the charge of the permanent dipole, the stronger the induced dipole, and the stronger the intermolecular force or bond. And that brings us to the last of the intermolecular forces, and it involves instantaneous dipole moments. We have seen the permanent dipole of molecules like water, the induced dipole that requires a charged particle, and now we are introduced to the dipole that springs up of its own volition. An example of such a dipole begins with the symmetrical distribution of electrons around the nucleus of an atom or covalent bond, just like the start of the discussion on induced dipoles. Here, though, we will think of electrons as rapidly moving charged particles. When, through normal motion, one side of the atom or bond has more than half of the electrons, an instantaneous dipole moment occurs. As a demonstration of this instantaneous dipole, consider the third electron in the 3-electron atom. It is drawn here pretty close to the dotted line that marks the halves of the atom. The positively charged nucleus is also sectioned into halves. We can argue that with this distribution, the two halves of the atoms each have the same amount of negative and positive charge. Both halves are neutral, but electrons are always moving, and at some point in time, the third electron will find itself on one side with another electron. The two halves will no longer have the same amount of charge. One side has more negative charge at the expense of the other side. One side is now partially negative and the other partially positive. This type of instantaneous or spontaneous dipole occurs in all atoms, in all bonds. It is the very nature of matter. The partial charges are very small and very short-lived. For completion's sake, we will look at how a bond can find itself in an instantaneous dipole. Here's the representation of hydrogen, H2, with the shared electrons drawn as stationary dots between the two atoms. But electrons are not stationary. At some point in time, the electron pair will find themselves exclusively on one of the two atoms. The once neutral molecule will now have a charge distribution and become an instantaneous dipole. Again, it is very weak and short-lived. Almost immediately, the electron pair will migrate back and the molecule will return to its neutrality. The question becomes whether the instantaneous dipole can participate in intermolecular bonding. The answer is a resounding yes. It is present in all matter-matter interactions at the atomic and compound level. These forces are called dispersion forces. All atoms and bonds have instantaneous dipole moments. It is just a product of the motion of electrons. Previously, we saw that the proximity to a charged particle like an ion or a dipole induces a dipole. How big of a leap is it to suggest that the proximity to an instantaneous dipole induces a dipole? Bringing back the H2 molecule in its instantaneous dipole form and putting it in the proximity to a neutral H2 molecule, the small partial charge of the instantaneous dipole can still influence the distribution of the electrons in the neutral molecule. The mild electron repulsion will have the effect of generating a small but relevant induced dipole in the once neutral H2 molecule. This is the weakest of all the induced dipoles. Still, an intermolecular bond is formed between the partial negative side of the instantaneous dipole and the partial positive side of the induced dipole. Being that the instantaneous dipole is so short-lived and so weak, the attraction only works over very short distances. The forces are called London dispersion or van der Waals forces. Although they are the weakest of all intermolecular forces, they are present in all matter-matter interactions. They explain how nonpolar molecules have attractive interactions. If it wasn't for these forces, all nonpolar compounds would be gases. They could not form liquids or solids. Dispersion forces bring up the rear on our list. They finish our list off. While we have the list up, we should ask, what is the overarching principle behind the ranking of strongest to weakest forces? It is charge. The weaker the charge, the weaker the forces. As weak as they are, dispersion forces do have an effect on physical properties, as can be seen with a few trends. One is that the larger the atom, the stronger the induced dipole. Larger atoms often have stronger dispersion forces. The more electrons an atom has, the bigger its radius. This allows for stronger instantaneous dipoles and stronger induced dipoles. Stronger intermolecular interactions require more energy to break. That is why there is a trend with atomic size and boiling points. Moving down the noble gas column on the periodic table serves as a good example of this trend. There is an upward trend for the boiling points of the noble gases following atomic size. Helium is the smallest atom and has the lowest boiling point, and xenon and radon are the largest atoms in the column and have the strongest dispersion forces, as evident from their higher boiling points. In a similar manner, bigger molecules have more electrons and a longer distance for them to travel. This results in bigger induced dipoles. Long, thin molecules can develop bigger temporary dipoles due to electron movement than short, fat ones, even if they contain the same number of electrons. This also results in higher boiling points for larger molecules. A look at boiling points of hydrocarbons as a function of the number of carbons shows the single carbon methane to have a low boiling point, well, lower than the 2-carbon ethane, which is lower than the 3-carbon propane. Butane and pentane continue the trend. And finally, it is easier for long, thinner molecules to have induced dipoles because more of the molecule can be approached. Geometry does have a role. 6 forms of intermolecular forces were covered in this lecture. As a recap, intramolecular bonds hold atoms together within a molecule or compound. They are strong bonds. Intermolecular bonds are between compounds or elements, are generally weaker. All bonding is a result of electrostatic interactions. The attractive and repulsive forces of an electrostatic interaction can be between atoms, ions, or compounds. Polar covalent bonds have their shared electrons spend more time around one of the atoms, forming a permanent dipole. Dipoles are often represented as an oval or an ellipse and given a color scheme to show the charge distribution. Ranking intermolecular bonds, or forces, was done by strength. Strength is related to the size of the charge, be it permanent or induced. Our ranking has the ionic bond as the strongest. Ions have full charges. Cations attract anions. As for trends, bigger ions tend to generate weaker intermolecular forces. This is seen with lower melting points. The higher the charge, the stronger the intermolecular force, and the more energy needed to separate ions. This means higher melting points. The ion-dipole attraction comes next. It has the full charge of an ion attracted to the partial charge of a dipole. These are important in solvation. Then there is a special kind of dipole-dipole interaction. It is the hydrogen bond. It gives water many of its unique properties. There are other types of dipole-dipole interactions. The partially negative end of one dipole is pointed at the partially positive end of another dipole. Trends with this interaction include stronger dipoles having higher melting points. New to this lecture was the induced dipole. Proximity to a charge, ion, or dipole distorts an atom's electron symmetry and induces a dipole. The weakest forces are the dispersion forces. Here, an instantaneous dipole moment induces a dipole. Trends are based on the capacity of an element or compound to form induced dipoles. Larger the atom or molecule, the greater the instantaneous dipole and the higher the melting and boiling points. And that completes our lecture. Remember, intermolecular bonding is about charge.